Hello, my students in grade 9. This is Ghassan Masadi, a science teacher at Taqarob International School. I hope you all are fine and healthier. First of all, I would like to thank all of the students who sent their worksheet solution. Today we will discuss the lesson 3 from chapter 14 under title The Doppler Effect from page 507 to page 512. Christian Doppler is an Australian physicist. He was the first one to describe the change in wave frequency during the relative motion between a wave source and observer. So we can define the Doppler effect for a sound wave as the Doppler effect, the change in the pitch due to the relative motion between a source of sound and a person hearing the sound. The most important things we need to know when we describe the Doppler effect are the frequency of source wave frequency at observer, speed of source, and the speed of observer. The Doppler effect occurs with all kinds of waves, not just for sound waves. And it's used in various applications such as astronomy, radars, medical imaging, satellite communications. In this lesson, we will study the Doppler effect on sound wave only. Because the Doppler effect depends on the relative motion between the source and the observer, we want to study the frequency of wave for both, for the source and the observer. I will divide this lesson as the following cases. Case 1, when we have moving source, stationary observer. When a source of sound moves toward an observer, the frequency heard is higher than the frequency produced by the source. And when a source of sound moves away from observer, the frequency heard lower than the frequency produced by the source. Now look at this figure. If we have two stationary observers and sound source stationary also, then all observers hear the same frequency. Suppose the truck moves toward the right as shown in this figure. The source moving toward to the right with the speed v, the source is equal v source. The observer ahead of the truck hear a higher frequency sound because the source is moving toward the observer. An observer behind the source, behind the truck, hears a lower frequency sound because the source moves away from an observer. We can conclude the frequency is higher when a source approaches an observer and lower when a source moves away from an observer. Now, suppose a source emits sound with a frequency f source and moves with a speed v source, and the speed of sound is v, the sound which is constant, is equal to 343 meters per second. We can calculate the frequency heard by an observer by using this equation. F frequency at observer is equal the frequency of the source divided by 1 plus minus V source over V sound. Be careful when you use this equation when you put plus and when you must put minus. The plus sign is used for a source moves away from the observer, and the minus sign is used for a source that moves toward the observer. As an example, to show how we can use these equations, we need to solve example 7 from page 509 and express a train sound is whistle as it approaches a station. The whistle produced a tone of 655 Hz and the train travels with a speed of 21.2 meter per second. Find the frequency heard by an observer standing on the station platform as the train approaches the station. This is the case 1. Case number 2, passes the station and moves away. In this example, we can get the following information. The V of the source, the speed of the source is equal to 21.2 meter per second. V of the sound is equal to 343 meter per second. And the frequency from the source is equal to 655 Hertz. And the question asked me to find the frequency at the observer. Now, when the source or the train moves toward the observer, we use the formula F observer is equal F source over 1 minus V source over V sound. And here we use minus because the source moving toward the observer. Then substitute your numbers where the F source is equal to 655 and the V for the source is equal to 21.2 and the V of sound is equal to 343. Put your numbers, calculate the denominator first to find this is equal to 655 over 0.938, which is equal, the frequency at observer is equal 698.15 Hz. Show that the frequency at observer is greater than the frequency of the source because the source moving toward the observer. In case B, where the source moving away from the observer, we can use this form of equation. F for the observer is equal frequency of the source over 1 plus. Here we use a plus because the source moving from away from the observer. So is equal 1 plus V source over V sound. Substitute your numbers. 655 over 1 plus 21.2 over 343. Calculate the denominator firstly. Then we can find the F at observer approximately is equal 617 Hz. In this case, the frequency of observer less than the frequency of the source because the source moving away from the observer. Okay. The question 36, page 510 is related to this example. If the stationary observer hears a frequency of 702 Hz as the train approaches the station, what is the speed of the train? From this, we have the same information about the first example. Frequency of the source is equal to 655 Hz. And in this question, give me the frequency at observer is equal to 702 Hz and ask me to calculate the velocity for the source or the velocity of the train. We use this form of equation because the train moving toward the observer. So the frequency for the observer is equal to F source 1 minus V source over V sound. Also, we use minus because the train is moving toward the observer. And rearrange this formula by do cross product. We can find 1 minus V source over V sound is equal F source over F observer. And we can write it as V source over V sound is equal 1 minus F source over F observer. Just change these in between two sides. Finally, we need to find the relation to calculate the V source. We can write the V source is equal 1 minus F source over F observer times V sound. Substitute your numbers to find the V source is equal 1 minus 655 over 702 times 343. V source is equal 0.067 times 343. This meaning the V source is equal approximately 23 meter per second. This is the description for case 1 when we have moving source and stationary observer. In case 2, when we have a stationary source and moving observer. In this case, when the observer moves toward the source of sound, the frequency heard is higher than the frequency produced by the sound. And when the observer moves away from the source of sound, the frequency heard is lower than the frequency produced by the source, as shown in this figure. When we have an observer moving toward the stationary source, the frequency may be greater than or increase when the observer moving toward the stationary source. But if the observer moving away from the stationary source, the frequency is lower than the frequency of the stationary source. We can calculate the frequency heard by a moving observer by using the following equation, where the F observer, in this case, the frequency at observer is equal to frequency of the source times 1 plus or minus V observer over V sound. This plus sign is used for an observer that moves toward the source, and the minus sign is used for an observer that moves away from the source. We need to take or to solve some examples related with this relation. Example number 8 on page 511. A street musician sounds that string of his violin, producing a tone of 440 Hz. What's the frequency does bicyclist hear as she approaches and moves away from the musician with a speed of 11 meters per second? In this example, we have the velocity for the observer is equal 11 meters per second. The velocity of the sound is equal 343 meters per second. And the frequency of the source is equal 440 Hertz. And we need to calculate the frequency at observer. Use the Doppler effect equation for an observer moving toward a source. We can use this formula. F observer is equal F source times 1 plus observer over V sound. And we use a plus because the observer moving toward the source. Substitute your numbers to find the frequency of the observer is equal 440 times 1 plus 11 over 343. Just calculate this ratio and we can find the F observer is equal 440 times 1.032, or the frequency at observer is equal 454.1 Hertz. And this is greater than the frequency of the source because the observer moving toward the source. In case B, if the observer moving away from the source, we need to calculate the frequency at observer. We use this form of equation. F observer is equal F source 1 minus V observer over V sound, because the observer moving away from the source. Substitute your numbers. 440, this is the frequency of the source, 1 minus 11 over 343. Then we can find the frequency of the observer approximately is equal 426 Hz, which is less than the frequency of the source because the observer moving away from the source. Now we need to solve question number 39 on page 511. It's related also with this example. If the bicyclist heard a frequency of 451 Hz when approaching the musician, what is her speed? Because the observer moving toward the source, we use this form of equations. F observer is equal F source times 1 plus V observer over V sound. And we know the F frequency for the observer is equal 451 and ask me to calculate the velocity for the observer. So we need to rearrange this form of equation to calculate the velocity for the observer. First of all, divide both sides of F of the source. We can get 1 plus V observer over V sound is equal to F observer over F sound of F source. And then move one to the other side. V for the observer over V of sound is equal F observer over V source minus 1. And we need to find F V for observer, to multiply both sides with V of sound to get this form of equation. V observer is equal F observer over F of the source minus 1 times V sound. Substitute your numbers. The F for the observer is equal 451 divided by 440 minus 1 times 343, which is equal 1.025 minus 1 times 343, and V of the observer we can find it at 8.575 meter per second. This is the velocity for the observer. At the end of this lesson, if we have any question, don't hesitate to contact me, and don't forget to solve the worksheet. Thank you very much.